All right, so let's start in on this. I am aware. Here, let me kind of run down the weeks first. I think I have Blackboard up and running here. Okay, so I know I'm pretty aware that like this is week 6, and hang on, sorry for the echo. I'm watching the stream on the phone at the same time. I'm aware that I'm going ahead a little bit. Week 6 deals with the end of chapter 12. So uh, if we go down to week 7, you'll see it's starting to prep um, for getting into chapter, um, I believe, 16. If you look at the homework, you'll notice what we're doing is we're going from 12 into 16, and then we're going to come back to 13. 16 is probably the most difficult. The end of 12 with the polar coordinates is probably one of the most difficult. Um, so now if I go to this 8, well, I guess 8 and 9, this is kind of where I'm at in the, the lecture space. Um, this one's a pretty good one to watch because it relates what happens in chapter 16 and relates back to what happens in chapter 12. Um, this one basically introduces it. This one we work a problem. And this one, of course, we work another problem and another, but I'm going to step. Okay, so let's go ahead and look at 8. I'm going to step in and take a look at, say, this particular problem here. But before I do, let's go back to the picture I had, which was the book, which is right here. Something is interesting here. If you look at a bicycle, and obviously someone used a camera and took a picture of this, and of course, as this person is riding the bike going from left to right here, what you notice is something kind of interesting. First of all, notice this spot right here. That looks like to me a reflector, but most reflectors are not shaped this way. However, this point right here seems to be moving in that direction, so it's streaking a little bit. Also notice the distance from here to here is larger than the distance between here to here. Not only that, but the tread looks like it's different over in here. That's because actually, when you took this picture, the ground's not moving. The person standing there taking the picture hopefully isn't moving. And what it determines is the only place on this bicycle that's not moving at that instant is something called the instant center right here. And they use IC a lot. What you'll notice is if you drew a line directly to the center, it appears as though that the bicycle tire is actually rotating about that point right there. So the center, that little bolt right there, is moving directly to the right. What you find out is you drew a line up to here, you would find this would be moving faster. And in fact, if you do a straight line like that, you're finding the same thing. Any particular one of these will give you the same thing. What I mean by that, any one of these, here's what I mean. That, say we just pick this one. Try to draw a straight line here. Any point, for example, this spoke right here, or that spoke right there, if you drew a perpendicular, it would be going in that direction. You move up here to say the base of the tire, or maybe that's the rim. There is a component of that going to the right, but there's also a component going straight down. So you don't see that here. This component right here is only going to the right. If you move back here at this one, there's a component that's going up and then a component going to the right. Oops, that was supposed to be a straight line. Perpendicular to it, that's what you get. So how can we use this? Well, let's go take a look at that problem, which I believe is right here. And it says determine the angular velocity of the link AB at the instant shown if block C is moving up at 12. So I'm going to have to copy this to paste it down over in, let's see, okay, let's see. So here, let's get rid of all this and just drop our picture right here. And we're going to go ahead and pick up the information here. I'll just drop it right there. Oh, maybe move it to the right. You know what I'm going to do too is, because I'm going to use a lot of graphical information here, I'm going to zoom in on this, get a snapshot of this so that I can use it for the graphics. Okay. So if we start looking at this, he says that the block at C is moving upwards at 12. Oh, I tell you what. Well, that's probably good enough. So this is 12. That's a piece of information we know. Now, we want to really know this. I believe that's what he's asking. The angular velocity here. Now, what I'm going to do is I'm going to go back and take another snapshot of the same thing using a different snapshot method. I'm going to move a little bit to the right. Okay, this time I'm going to use that little okay. Go back over here and we're going to drop this one right here. Oh, interesting. That's different. You know what? That was unexpected. So I guess the old style snapshot looks different than the new. Okay, let's take a look at just this. If in fact this is what's happening, that it is rotating in this way, this particular point, rotates like this. And you could draw, oops, okay, here, make use of the ruler. You could draw a straight line, and then, see, 24. You could draw a series of points along in here. And say to yourself, each one of these points is moving like this. So this tells me that the velocity at point B, its value is the omega in radians per second times the length from A to B. So it would be omega r. In this case, it would be unknown radians per second times a length, but we do know the length there, and for that matter, I believe, let me make sure, he did. He said in inches per second. So we're going to leave all of our speeds in inches. So that would be inches. Now, don't know what that is. That's what I'm supposed to find out. But I'll just sort of hang out there for a minute and say, hey, you know, this is what we're going to find. I'm just going to carry it along for the ride. Now I'm going to do something interesting. Well, one of the things, okay, so I'll take a side issue here. I don't think it's that important at this very instant, but it might become more important later. That is, this is 45 degrees. That one's 90. That's 45. So that's got to be 45. So there's a whole lot of 45s here. So if you really wanted to break this into the x and y components, you could use your 45 degrees. We're not going to use that at this very instant, but we might use it later. So now let's look at the second link. That's this link right here. And in order to do that, I think what I'm going to do is go back, take a look at the diagram as well. This time I'm going to take the right end of that diagram. And now I'm going to slide a little bit further to the right, and I'm going to drop that down there. Now here's something interesting. Okay, I think I did graphically okay with this. It's possible maybe I could have done better, but I'm going to make use of my abilities there, or my nice picture, and say to myself, hey, I'm going to, I believe, is this it? Yeah. I am going to try my best to just simply copy that, Control C. I'm going to move over here somewhere and just maybe drop it right there. But this time, I'm going to put that vector right there at B. Now, why can I do that legally? Well, I can do that legally because this point is the same as that point. They have to be going the same velocity in the same direction. So I've got that. I've got an orientation, 45 degrees up. So if you really wanted to look at it and be particular, you'd realize this has got to be 15 degrees. So that makes this whole thing 45. So I think we're okay there. So it looks, I could get out something and measure an angle, and actually if you use this ruler, I think you can. Let's see if this is actually 30 degrees. It pretty much is 30 degrees. Is the other one 45? And it's off a little bit, but it's reasonable. We're going to make use of that in a minute. I'm going to hide the ruler and come back to it. Well, you know what? I'm going to go ahead and use the ruler the rest of the way out. So here I know, I know this goes straight north. Meaning that this is going north, and I think it was 12 inches per second. I know that's 45 degrees on point B because it says it's 45. So what I'm about to do, I'm about to use a weird, here I'll use this blue. The blue is going to be indicating the perpendiculars to the velocities. Here's what I mean. So this is point C. And point C has a perpendicular. I'll make it go out a little bit more. Here's your perpendicular to that velocity vector. Now, let's find a perpendicular to that velocity vector. Now, we knew it was 45 degrees. And so it turns out this particular point is the instant center for that link at this instant. This link appears to be rotating about that point. We're going to work it both ways, and I'm going to do something I think that is, let me see if I've got this. Oh, I do. Okay, I have this CAD package that's out here. Let's give it a minute to come up. I'm going to draw this geometry when I get to that point. This is not the fastest computer, so first, and you'll see why I'm doing this in a second. First, let's go back to the original geometry. I'm going to call this the origin. So it means I have to draw a link at 45 degrees down there. 45 degrees, so I'm going to draw point A, point B, and point C. And then I'm going to connect them with a straight line. Nothing fancy there. So there's a couple things I could do. One, I could do a working plane. The other thing I could do is figure out the distance in X. Maybe I'll do that so that I don't have to do a working plane. For those of you who know how to use CAD, the working plane idea can be good. Let's see, I'm trying to think if I should do that. Maybe I'll do that. It may take me a minute to figure, i.e. remember that. But first I'm going to draw just a straight line. And what I'm going to do, I'm going to go from 0 to say 10. These are going to just be reference lines. And then what I'm going to do is I'm going to go from 0 to 10 in that direction. And then what I'll do is I'm going to do a zoom out. Okay, so this is going to be my point A. And the next thing I'm going to do, I'm going to make my black line be, now I know that 45 degrees is going to be like so. If I move over, move to the right, that's where I'm going to be. Turns out now if I measure this line, with a dimension, you're going to find something interesting. I'm going to make it free form, and you're going to find, oops, I have to hit that and hit here. It's not going to be of length 5. So if I want it to be of length 5, what do I need to do? 2 or 3 things I could do. Let's see. It may take me a minute to find this, or it might be better for me to just go ahead and do octave. And then say I want to know what 5 divided by the square root of 2 is. Okay. Do format long so I can get all the digits. So now what I'm going to do is I'm going to copy this big long number, and now what I'm going to do is go back and delete that line, delete that dimension, create a new line. I'm going to go from here, and I'm going to go, oops, wrong thing. I'm going to create, I'm going to create this number, and then I'm going to create a minus that number. Okay, so now if I look at the dimension now of that line, freeform dimension, oops, you'll see now it's of length 5. Why is that? Because the distance, the x distance from here to here, is 5 divided by the square root of 2. If you look at a triangle, that's the case. Now I need to do the second link, and that starts here at the end, and it moves at 30 degrees to the right. Okay, so here's what I mean. So it's 4 inches. So if I were to look at the distance here, let's get the ruler out of here real quick. I want to know if I measured what's the distance here. It's 4 cosine 30. What's the distance up to here? 4 sine of 30. So let's get those two numbers ready, and then we're going to draw point C. So 4 times cosine degree 30, 4 times sine degree of 30, that should give me 2, yep. So the y is going to be 2 up, the x is going to be that distance. Copy. So what we're going to do is we're going to go back to this. I'm going to draw a line. It is going to start here, but let's see. I can't remember. Okay, dx, that's correct. I want to go from the last point, relative, I want to go a distance up at 2, and I think it's still in my buffer. Looks like that. Now, I want to go in dimensions, make sure that I've got that correctly. Oops, wrong spot. Okay, it is the correct. So that's the correct length. That's the correct length. Let's see if I can make sure the angle is correct. Now, sometimes I don't quite get this correct. Okay. Okay. Looks like it is exactly 30 degrees. So I've got the actual geometry here. The big deal here is these are the two links. I'm going to go ahead and mess with them. Sorry for it being so slow. Make them pretty thick. Now what I'm going to do is zoom in on them, and I'm going to do something interesting. Most CAD programs have something like this, and they'll say draw a perpendicular line to an existing line. So it says end point of the perpendicular and the existing line. So I'm going to pick, first of all, I'm going to change colors to a red, say. So there's, oops, there's the thing. There's the existing line. Oops. Mistake, mistake, mistake. Try that again. And what we'll do, so this line, I need to take away the point editing. And now, let's do something interesting. We will now draw a vector. Oops. We're going to draw a vector along that line. And we're going to take that vector, take it off of here, and get rid of that. And we're going to place the velocity vector here. So this is actually perpendicular to this line. Again, this is point A. Maybe make it capital A. So here's your point A. Here, in fact, is your point B. Zoom out. Oh, I don't guess I can. Take that out. Okay. So this right here is point B. This right here is point C out here. I may move the C's around. Turns out I know the velocity of C goes directly upwards. Okay. So what I need to do now, this sounds weird, but I need to find perpendiculars to the two velocity vectors. And in the lectures that are online, you'll see exactly why. But in fact, I can go back and review that for a second, and that basically relates to the fact that if you had a blob and it were rotating, say, about, if you found any two velocities on that, let's just say I don't know that my vectors are proper, but anyway, if there are any two velocity vectors that you know, their magnitude, direction, and their location, of course, then you can actually determine the instant center, and you can determine the rotation, the omega, about it. But this is all based upon finding any two velocities, drawing perpendiculars to them, finding the intersection. So this is what I'm attempting to do right here. Now, let's go back to my drawing here. that I have right here. If we look really close at this, and now we're to find the distance, say distance 1 from here to here, and then distance 2 from here to here, then that tells you that this velocity at c, and I can say it's just the magnitude, is the omega times the distance 1. So if I can find this distance 1 in like a CAD drawing or using trig or anything like that, then I can determine this, because if I can determine this and determine this, I've suddenly got the omega of this link. Appears like it's rotating right over here. Omega BC. Once you have that, once you have omega BC, you can then use something else you found, which is d2, to find this velocity. Let's now go and find d1 and d2. And we're going to find it off the CAD drawing. Now, how do we do it? I'm going to change my colors to yellow. I'm going to go back and find a perpendicular line. I am now just going to go out here and I'm going to find a perpendicular to that. Now what I'm going to have to do, I'm going to have to grab the end point right there and move it to that end point. Now what I'm going to do, turn around and do the same thing. Pick a point out here. It has to be perpendicular to that velocity vector. Now, oops. One of the things I might want to do, let me turn off. I'm going to hit the layers. There's a way to save a layer by colors. They have changed this. In any case, what I'll do to take care of this is move these links out of the way for the time being. So I'm going to move them out of the way. I can move them back. My yellow line I hit the wrong way. I'm going to go back and do a perpendicular. I'm going to be out here, and I'm going to be perpendicular to that. So what I need to do, select the end point of it, put it right here. At this point where these two yellow lines cross, right there is the instant center. Now it looks to me, I'm looking on the stream and realizing kind of hard to see, so I'm going to make them a little bigger. That's the instant center. So what do I need to find? Well, here, let's do this first. Let's do this, and then I'm going to zoom, and I'm going to say there in fact is our triangle. What I need to do now, these things are kind of difficult. The red vectors are in the way. Let's just say it that way. If we look back at the drawing, I'm looking from C back to the intersection and B back to the intersection. These two vectors are kind of in the way. They have nothing to do with it. I just need to find the length from here back and so on. Easy way to do that, the easiest way, is to pick a color, draw a line, or another way to do it is just draw any sort of line or draw a vector, say, and then try to draw a vector to that intersection, but there is a way to find intersection of two lines, and that would be in a point intersection. I don't remember if it's F4 or Shift F4. Okay, so now it says, there we go. Just like that. So now that I have this, I have a point location I can get a dimension off of. So I'll get a dimension. I will do freeform. I'm going to get the dimension from this point all the way over to that point. And then I'm going to get the dimension from that same point to the end down here, and that's what you get. So let me look at that. 5.464. Now we're going to find this by trig in a minute. 5.464. So this number, I'm going to go ahead and use a pen. This number is 5.464, and so I'm going to take this out, move it down here a little bit, oops, and just erase it. 5.464. Okay, the dimension over here was 2.828. This one, 2.828. That is the dimension on the other one. So let's take a look at this. Okay, so you got an object. It's rotating here. Let me erase this. Let me erase this, and we're going to redo it. The velocity of c, which is equal to 12, is equal to the omega of this length, which in this case is just BC times the distance there, 5.464. So this means omega BC is equal to 12, 5.464. Don't know what that is, but we can figure it out. .464. It's got to be another digit there. 5.464. 464. Nope, no other digits. 2.1962. 2.1962 is omega BC. Now, if you're over here, the question is, what is the velocity of B? Actually, it's equal to omega BC times a different R. So what you have to realize is this is the R between the rotation center and the point. Now the rotation center is at a different point, and it's 2.828, which gives me the velocity of B is... Okay, what I can do here is take that times 2.828 gives me back 6.21. So now I can translate back here that the velocity of B is 6.21. Now I can just slip omega AB underneath there, And it will be 6.21 divided by 5, or and I'm pretty sure 1.24216. 1.24216. I'm pretty sure that I've thrown away some digits there. Let's go back and see from the blackboard. If I put the answer in this, okay, so what you see is 1.24, and we ended up with 1.24. So we ended up with the same thing. Now, those digits were long since forgotten, apparently. So the key is if we look at this link, this is particularly the key here. Is if we look at this link, it appears as if this link here appears to be rotating around this point, which is the instant center, which is the point it's where it's rotating about. So everything is fine there. So that's pretty much it. Now, in the book, off of this diagram, more than likely they'll use trig to get the answer. Okay, so if I take this and I bring it down here, and I bring it up here, say, first thing is this line, okay, not sure that I need this, but 30 degrees, 4, and then the question is, what is that line? This line is, from a vertical standpoint, it's 45, but that makes this, okay, you have to realize this is 30, okay, these two are 90 degrees, so 90 minus 30, oh, I gotta move that 4 out of the way. Okay, 90 minus 30, 60. So it looks pretty ugly here. So I've got a length. God, that looks ugly. So if you think about it, a length, an angle, another angle, because really this one's 30. Okay, so if that's 75 plus 30 equal 105, I think. Take 180 and pull that out. That gives you the other angle. Then you can start using law of sines and find these distances. I don't know why I have this drawn up here. So you should be able to go in and find everything there. You also should be able to go back if you had a CAD program, and some people do and some people don't. So if I'm sitting here looking at this, okay, all right, now, all right, hang on. It's very hard to tell you what. I'm going to drop that link back on here, and then we're going to zoom in on this triangle. I'm going to go ahead and be lazy and go into dimensions off of the angle. So what I'm going to do, go out here, and then, oh no, I should have done the other one. Let's say we'll go out here. Oh, wrong. I was doing the right one, sorry. Oh, okay, yeah, yeah. So in fact, that shows it to be 105. That angle being 105, we can't make it, maybe I can make it go down. Okay, boy, this is bizarre. Oh gosh, now it's showing 255. Now it's showing 105. Okay, so it's showing 255 over there. Oh gosh, or 105 there. Let's see if I just click that. I can't even tell where things are here. So anyway, you can use law of sines and cosines to figure this out. It would have been nice to have, it's possible maybe I could do it. Try this again. Dimension, angle, extension, color. It doesn't show that, let's try it again. I'm wasting time here, but okay, so I keep going out to here and say pick that location, call it good. It listed up there at 105. Okay, so this one, that's fine. So I misspoke on one of those. Then the other angle, this should show to be 30. So if I hit here and hit there, but apparently I need to hit in the other direction. Hit there and hit there. This one shows to be 30 degrees, and this is particularly odd. This is an issue with the CAD program here. But yeah, that's 30 degrees, 105, and then 180 minus 105 minus 30, which that you could find that out if you wanted to dimension it. But I'm beginning to waste too much time. So so anyway, you can determine all of this. That's actually a 45. That's why I goofed up. So it's 60, 45 gives you 105, and then what, 70 something like right up in here. No, okay, 180 minus 105 minus 30, and that would be the angle that would sit right here. So in fact, you'd know this angle, this angle, this angle, and this distance. If that's the case, you can use law of sines to get that distance and to get this distance. And those are the two distances you need in this problem. So what I'll do next time, I think, is I'll come back and work that problem the old way, and I'll work all these problems both ways. And maybe next time, instead of drawing the CAD package out, I will work on just doing the trig method.